All right, everybody, welcome back. For everybody on Twitch, welcome back. We're into lecture 19. So as we wrapped up on Monday, we're going to start more of the math section of the class where we learn how to use Matlab to solve equations, right? It's more of a practical use of Matlab because that's the kind of stuff that will come up a lot in a lot of the remaining classes that you have here in engineering and science in general. So we're going to spend some time on that. Today we're going to split it between sort of two aspects. We'll take some notes over in Excel and see how to use Excel's method for solving for an unknown. And then we'll come back over and do the same thing over in Matlab and learn a little bit about some of the, on the one hand, odd syntax that we have to use, but also on the other hand, very sort of regular and repetitive syntax that we have to use to solve these things. If you ever want to do this in Excel, which I bring it up because it's so useful to do it in Excel, you need a tool called GoalSeek, which, let me switch over here. In order to get goal seek, it's already in your distribution of Excel. Just depending on which version of Excel you have, it may be in a slightly different place. So here I search for Excel goal seek. Just find the one that's for Microsoft and it'll say use goal seek. Somewhere down in here, either both in Windows or Mac, if you scroll down a ways, it'll say, okay, now you need goal seek. It's kind of buried. It's in the data tab, data tools, what if analysis, goal seek, right? Kind of down in there on the side. I have a tendency to put it on my quick launch toolbar so that it's always just up on the top. It's a real tiny icon because it's so useful. It's a really nice thing to have. So I'm just going to copy these instructions so that when you see our notes, if you need goal seek, it'll be there. You don't need it immediately, like you don't need it today necessarily, although today is probably one of the few times that we'll use it. We probably will only use it one other time, but I want you to know that it's there and we'll at least demonstrate what it's doing. So I'm going to switch back over to Excel and we'll take a couple of notes and then solve some problems. Zoom in a little bit so that you can see this. So this is how to get goal seek. On Excel. I believe that will be there as well on the online version. So if I go into data here, it's actually, their instructions may be off from whatever your version of Excel is. I don't have to actually go to the data tools group. It's over in this forecast one under what if, and then goal seek is over here. Hopefully you can see that on Twitch. I'm not sure if you can see the pop-ups on there, but at any rate, it's on the data ribbon over here on what if. But as I said, you can also add it to your quick launch bar. So I've got it up here in the top left so that it's just there whenever I need it because I never remember where it is. So we'll come to that in a little bit. If you haven't found it yet, that's okay. We'll have more time to do that. Our topic for probably today, Friday, we don't have class Monday, and then we'll probably talk about it again on Wednesday and possibly even the Friday after that, is root finding, which if you've never heard it called root finding before, you've probably heard it called solve for x. It's the same problem. Whenever we have an equation with an unknown and we have to solve for that unknown, we might call that like a solve for x style problem. The process that you're doing in there is called root finding. And we'll talk about why it's called root finding here in a minute. Generally, the type of root finding we're talking about here is for one equation and one unknown. So we will get to root finding with more than one equation and more than one unknown, but we're restricting ourselves to just one for now. And this comes in about 5 basic steps, really 4, because you don't really have to do the one all the time. Let me adjust my columns here so that they look a little bit neater. The first basic step, this is the one that you probably won't have to do too much here in CENG 15, but I write it down because it's not necessarily like a gimme. It's not trivial, but you have to identify the variable and the equation. Right? That seems like it should be, if I'm going to solve an equation for an unknown, I need to know what the equation and the variable are. But that's not necessarily easy to do, right? I'm thinking if we dump you in a thermo class or a fluid mechanics class or something like that, finding the right equation and the variable is a task all unto itself. That's what we teach you to do in fluid mechanics. Once you've got that is then where you come over to what we're doing here. So the thing that we're doing here will not help you develop those equations at all, right? Those come from the physics of whatever it is you happen to be studying. For the most part in here, you'll just be given the equation and the variable, so it's less of a problem, but I point it out because it's still important. Once you've got the variable and the equation, you can kind of leave the other class aside and then think about what we taught you in this class, which is steps 2 through 5. You start off by rearranging the equation into what we call root finding form, or RFF. So for example, suppose the original equation was a very general one, and it was something like f of x is equal to g of x. right? Two very just general, any kind of function you can think of for x on one side and any other kind of function for x on the other side. Implicit, explicit, it doesn't matter. Well, there's one requirement, and we'll talk about that in a minute. In root finding form, that just means put everything on one side. So in this case, the way that I have a preference for doing it is to put the 0 on the left. So you would have something like g of x minus f of x. Or equivalently, you can move everything over onto the left-hand side if you want. So you could have something like f of x minus g of x is equal to 0. These are equivalent. Whichever one you feel more comfortable doing, or whichever one requires less algebra, you end up with the same answer regardless of which way you rearrange that equation. Although some of the intermediate steps, as we'll see in a moment, can generate slightly different intermediate results. Third step, guess an initial solution. We usually do this in one of two ways. The first is if you know nothing else about the problem, like let's just say it's a pure math problem, right? It has nothing to do with any physical situation or something like that, plot it. So that's the one that we're going to focus on in here. Is plotting it. Partly because a lot of what we're doing is just math, and I wouldn't expect you to know the physical significance of any of the parameters or what their typical ranges are. But also because I want you to practice, plotting and adding numbers to plots, and it's a good way to visualize your results. The other one is somehow that value, that initial solution, is implied by the problem. So there I'm thinking of examples like, you go into reaction engineering and you got to solve for a temperature, and you knew the inlet temperature was like 400 K and it was exothermic, so it had to get a little bit warmer, so you guessed like, I don't know, 450 or something like that. Something about the problem gave you some information that makes you think that a solution is somewhere. That's another way to do it. The implied by the problem, it won't so much be here until we get to multi-equation systems, or I should say systems of equations. Once you get to systems of equations, i.e. solving more than one equation for more than one variable, plotting becomes really not very helpful, because once you get beyond, like, 1, you can get a line plot, 2, you can get a surface plot, 3, there's no plot that creates something like that. We can't have 3 independent variables and still visualize it particularly well. And so we often rely on the problem to make our initial guess. The fourth one is that we iterate until we get close to 0. And I put close to 0 in quotes because there's some flexibility in exactly what we mean by close to 0. And it's usually set by the algorithm. So close to 0 can mean different things, and it can be adjusted. The default is usually around 1e to the minus 6 or 1e to the minus 8. So what that means is when the computer sees something like 0, let's say 0.1, 2, 3, 4, 5 zeros and a 1, or it sees something like 1, 2, 3, 4, 5, 6, 7, 1. It sees both of these as approximately 0. For the purpose of solving your equation, it says, I was supposed to find an x that makes this root finding form exactly 0. I got close, right? I'm 10 to the minus 6 or something like that. You're not going to be able to find an exact answer like you would if you were to try to rearrange it algebraically. So for example, the answer might be 1/12, and you might end up getting something like 0.083334, something like that. It ought to be really darn close, but it will not match perfectly. And it also doesn't matter the fact that we can't do 1/12 in decimal form, even if you had something like 1/2, you might end up getting something like 0.49998. Right? What we're doing is a guess and check, an iteration, and it is a numerical approximation of the solution. So the more times you guess and check, the better your numerical approximation, usually to the point where it's got so many digits of accuracy you just don't care anymore. We just kind of give up on it. Well, we don't give up on it. We say, yeah, that's plenty. I don't need anything more than that. And then the last but not least is check your answer, which comes in two flavors, and we'll use both of them. One is to plot the root finding function, which we've actually already done in 3, and then we'll overlay the solution as a point. So we'll practice doing that. And we'll also use the title, or just generally print the number, e.g. in the title. And we've seen how to do that before. We actually had a homework problem where you had some, like a spinner in Excel or a slider in Matlab, and as you adjusted that, it would recalculate a new value of f of x, and then it would take that value and display it into the title. The types of plots that we're interested in getting are all going to look fairly similar, so we can sketch out what those might look like here. Let me give myself a little bit more space here. So we'll always have labels. They might be really simple labels like x and f of x. There'll be some kind of a plot. That's a bad plot. Let me draw another one, something like that. That would be the root finding function, and then we would overlay the solution as a point. So for example, we might put a red dot there wherever we find it, find the answer. And then the title might be something like f of x sol, whatever the solution happens to be, is equal to some number. Where when we have that x sol, what that refers to is what's the value of x here at the solution. It'll also be helpful for us often to put a line that indicates the 0 axis, or a 0 value on the y-axis. So we will often throw a 0 in here like that, just so that we can see it. It makes it a lot easier to find the root, to find the solution, initially, if you can see immediately where that curve intersects 0. And adding that 0 line is not particularly a lot of code inside of Matlab, so we will add that pretty fast. And those are the 5 steps, really 4, because we don't need to do the first one. And what I'm going to ask you to do, in fact, when homework 4 gets posted, you'll see it'll probably be posted on Friday. When homework 4 gets posted, up at the top is a request. That request is to type out these problems. So I know a lot of the pattern here is going to be very similar from one problem to the next, and so you're going to be tempted to take the stuff that you wrote on the previous one, copy paste it into the next one. I will have no idea if you do that. Like when I go to grade your assignment, it will look the same. I can't tell whether you pasted something in there or not, but I'm going to ask you to try really hard to resist that temptation, because this pattern shows up so often in so many other classes that it's good to practice it as much as you can. So it's not that you can't go look at the other ones and sort of refresh your memory, but so much of what we're doing in here is central to so many other analyses. Try to take your time and think about where all that code is coming from as you're typing it, so that you remember what goes where, and you don't rely on having a template behind you that you can just copy paste. Again, I won't know. It's just my strong suggestion to you to try to do that. A few last comments versus and a little bit of guidance that you might want. The first part is that you want to use the plot from step 3 to look for multiple solutions. And remember, anytime we say solution, we also mean a root. A root, if you think back to your math class, is any value of x that makes f of x 0, or in our case, any value of x that makes a root finding function 0. If you have multiple roots, this will require multiple calls, multiple, let's say, solutions, which I guess sort of stands to reason, right? If there's more than one, well, okay, that's redundant because I said look for multiple solutions and it will require multiple solutions. We'll need you to run root finding process multiple times. Anytime you run the root finding process, you can only find one root at a time. So if there's more than one, you have to run it multiple times. A second one is that we're going to use local functions in Matlab for your root finding functions. So you'll very quickly see that I reuse function names a lot. So you'll see something like my function or my root finding function or just RFF, etc. That's actually one of the advantages of the local function syntax is we can reuse those names over and over and over again. So you don't have to come up with something like my root finding function for problem 1 and then my root finding function for problem 2. You can just say RFF or my function or something like that and reuse them. And last is just as a general comment, if you're ever looking to use these methods, the function has to be continuous. That doesn't mean that it has to be like a smooth-looking function. I forget those rules that you learned back in algebra, but there's like the horizontal line rule and the vertical line rule where like if the function passes through the horizontal line more than once, it means something. I don't remember any of that, but it's fine if it does that. So if you have a function that looks like this, that's perfectly fine. If you have a function that looks like a circle, that's also perfectly fine. The kind that it can't handle, I mean, it could even be a spiral too if you wanted to be weird about it. This is also fine. The one that it can't do is a function that does something like it comes over to here and then it jumps up and then keeps going. That one's no good. It can't solve those. The problem with that one is it'll get stuck bouncing back and forth on either side of that discontinuity. There is a way, which we'll see probably on, I don't know, Monday, something like that, where if that were the case, you could lock it to this range. So it would be okay if you had a discontinuous function, but you were looking for a root in its continuous domain, or its continuous range, that's fine. That's just another way of telling MATLAB, don't worry about the discontinuity. So this one would be okay, right, if you were to restrict it to just a subsection. All right, that's the end of our notes. We're going to solve problems now. So these are our notes. More people who don't want to do MATLAB. We had one this morning, too. I blame ECE because I think they're over here at the same time as us. And I think they try to get into that room and they accidentally come into this room. I think that's what's going on. All right, so I'm just going to wait here for a second. We're going to do an example. If you don't have goal seek, take a moment, see if you can at least find it, because we'll use that on the next example. So I'll just wait a second. Also, if you happen to be on Twitch, I am over in Canvas chat if you have any questions. All right, we're going to give ourselves a new sheet. We'll put an example on here. And we're going to practice going through those 4 or 5 steps, really just 4, so that you can see each one worked out. So the problem statement in here will probably be about as simple or as straightforward as find the roots of something. Remember, whenever we see roots, we think solutions, right? Find the roots, i.e. find the solutions of the equation x is equal to cosine of x. which is something that we already saw once. I think that was actually twice. I think we saw that on homework 1 and homework 2. You iterated a little bit manually with your clickers and your spinners to try to find the roots of that equation. So what would we do if we actually needed that root? Well, if we strictly wanted to follow those rules, step 1 would be to identify the variable. The variable's x, and the equation is x is equal to cosine of x. So you can understand maybe now why I say we don't really need that in this class, because most of the time the variable in the equation will be obvious. But in other classes, that step 1, will probably take you the majority of the time. Or hopefully it will, right? Because then you'll be done with this class and you'll know what the root finding stuff comes to after that. So it'll be easier. Next step is rearrange to root finding form. Again, we have 2 options here. I have a tendency to put the 0 on the left because of how we write our functions in Matlab. And so we would have something like 0 is equal to cosine of x. But we're going to think of this in a slightly different way. We're going to think of it as some kind of a target value is equal to cosine of x minus x. And here, what we're going to ask the computer to do, and what we're going to do partly by hand, is to vary x until target is close to 0. That's the structure that we're after here. We know algebraically when we rearrange that, it's got to be exactly 0. But we're not going to get it to be exactly 0. We're going to try to get it very close to 0. And we're going to try to get it very close to 0 by just generating lots of values of x's. Our third step, plot the root finding function and find an initial guess. So I'm going to give myself a little bit of space because we're going to have another one here. And we'll just plot this down here. So we'll have an x value and a value of the root finding function. I'm going to go from about -2 to 2. So I'll say -2, and then we'll just take that value and add like 0.01 to it. Actually, we'll add 0.1 to it. The plot doesn't have to be terribly accurate. And then the root finding function is just whatever that is, whatever the root finding function is evaluated at that x. So for our case, it's cosine of that value minus that value. Right, we're just evaluating a function here. It just happens to be called a root finding function. So I'll drag this down. We'll go to about +2. Oops, I did that last time. Let's see how close that got. Pretty close. A couple more to get us up to 2. One more. Again, we're just using the plot at this point to look for the solution. It's okay if it's not a particularly accurate plot. It doesn't need thousands of data points or something like that. But then we're going to go ahead and plot this. So I'll insert a line. Remember, we're trying to follow the STEM convention as best we can, where we're plotting a function, so it's going to look like a line with no points on it. And so with this figure, we say, where do we think it crosses 0? Well, the 0 is along the axis here, and it looks like our curve crosses somewhere between 0 and 1. You can be pretty sloppy with the initial guess in most cases, so I'm just going to guess that it's around 1. So we're going to guess around 1 for the root, i.e. for the solution. Again, we can be pretty weak with our guessing game on there, and the algorithms will help us out. The last part is iterate, or second to last part, I should say. Iterate until target is close to 0. We're going to pretend to be the iteration algorithm right now so that you can see, at least in concept, that it is just this simple. It only really requires 2 things. It requires a guess, and it requires a value of the root finding function. So we guess x is close to 1, and we calculate the root finding function for that value of x, that guess of x, so cosine of x minus x. The reason 0 is always used in these root finding functions is because the sign of the root finding function evaluated at your guess helps you a little bit. Here it says, all right, at x is 1, my value is negative. So let's go the other direction and see if we can get it positive. So 1 is maybe too high. If we go to 0, now the value is positive. So on one side of our guess it was negative, and on the other side it was positive. So our solution has to be in there somewhere. That's something that the root finding or the algorithms for root finding often rely on, is just checking the sign and going to one side or the other of the sign. But all it's going to do is guess. So 0 is too small. Let's try 0.5. It's got to be a little bit bigger than that. Let's try 0.7. We're getting closer. Now we've got 1 0 on there. Let's try 0.75. A little bit better, right? We're still a little too far, but we went over into the negative side, so we know the root has to be a little bit before that. Try 7.3. About the same, just in the wrong direction. How about 7.4? 7.4 is not bad, right? So within about 6 guesses here, we've already got about 1e to the minus 3 precision, which is not bad, right? If that's our algorithm, if that is quote unquote close enough to 0, we say we're done, and the root is 0.74. That's if we want to do it by hand. Of course, if we now put this into either Excel or Matlab, we can ask it to be much more precise in how it calculates this. So I'll show you once here in Excel, and then we'll switch over to Matlab. Unfortunately for the folks on Twitch, you're not going to be able to see my pop-up window on here, so I'll take a couple of screenshots and show you what we're looking at. What we want to do, you can click anywhere with your mouse. Go into Data, What If Analysis, and then Goal Seek. And I'm just going to take a picture of what's showing up here. And what you should see is a box that looks something like that. That's a little bit bigger than it needs to be. And it's more or less telling you exactly, it sort of reads almost like a sentence. What it's going to be able to do is set a cell equal to a value by changing a cell. That's what we're after, right? So this cell that it's referring to here, it's not A21. We want to set our root finding cell, right? That's the one that we're interested in. What value do we want? Well, we're always going to want to set it equal to 0. Goal Seek is one of those actually somewhat rare root finding tools that you can put in a number there. It will allow you to put in, 6 or 3 or something like that. And then internally behind the scenes, it will move that 3 over to the other side. Most root finding functions, algorithms don't do that for you. So it's kind of nice in Excel. But at any rate, we're always going to have it set up in root finding form. So we'll always just type a 0 in there. Which cell do we want to change? Well, whatever the contents of this is, has to refer to our value of x that was up here. This one. So we want to set the root finding function equal to 0 by guessing x, by changing cell x, which in our case is cell C19. So I'm going to go ahead and do that. Like I said, on Twitch, you probably won't be able to see this, but I will put the results in there. I'm going to say set cell C20 to the value of 0 by changing cell C19, because that's our x, and then I'll click OK. Let me take a picture of that too. So what we get is Goal Seek did find a solution. If it ever has Goal Seek did not find a solution, my initial guess, knowing nothing else about your workflow, is you probably didn't plot it. Because if you plotted it, you would probably have seen that there was no solution in the area you were looking for. Otherwise, you've just got a very poorly behaved function. So this is your answer. Right, that's the root. Or, excuse me, sorry, that is not the root. The root is on your sheet a little bit further up. That's just saying how close did we get to your answer. The answer itself is right here. And if you look up in the formula bar up here, you can see that it's actually known to quite a few more digits of precision than is displaying on the actual cell down here. But I mean, how often in engineering do we really need it? More than 3-4 decimal points? Not that often. I mean, it's there, but we don't often need it to too much more precision than that. This is really helpful, primarily because when you're using it in other classes, you can have really complicated steps in between this is my variable and this is the result. So for example, in your homework, one of the things you're going to have to do is remember that stair-stepping operation that you did before? That doesn't maybe strike you as something like a continuous function because you've got that weird stair-stepping process in the middle. But it is actually a continuous function for whatever you put as the bottom versus the top, right? They will always move in tandem with each other. They will never suddenly jump to another value. And so you can use root finding to say, you know, find a value of the lower one, which makes the upper one some value, right? You can turn that into a root finding process and still use exactly these same tools, despite the fact that you have to do that stair-stepping through it. And that can be extremely helpful in a lot of different contexts. But what we're going to do now is take this, put it over in Matlab, and look at the basic syntax for solving these in Matlab. That's primarily where we'll do stuff going forward. But I'll pause here in case anybody's got any questions or needs to catch up. I guess the last thing I'll do is if we were to annotate this plot, which I'm not going to do it, we would put a dot right here. At the very least, we would put a dot right there. But I'm not, it's actually, I think, faster to annotate things in MATLAB than it is Excel because it's easier to add stuff to your plot. Or I shouldn't say it's easier. I think it's faster to add things in MATLAB, but at any rate, I'll leave it as a dot here and we'll wait a second before we switch over to MATLAB. All right, so nearly every time that you're going to solve these, they're going to follow that local function syntax. So we're going to have a script portion and a local function. So I'm going to give myself a new script. Let's save it as something so that I don't lose it. I'll save it as example 2. And we're going to go through those same steps that we just talked about a moment ago. So the first thing we're going to do is write the function. Usually this is done by hand, so we're not actually going to do it here. There are some ways that if you're doing a live script, you can actually write the function in there, like so it looks like math, but we're not going to bother with that. Then we have to rearrange it to root finding form. Again, usually done by hand. There are some computer algebra, or there is a computer algebra system inside MATLAB that can do the rearranging for you. I don't know it well enough to teach you how to use it. I don't use it very often. It's not that hard to rearrange it to root finding function, right? You just throw everything onto one side. Then we're going to plot the function, plot the root finding function, to look for roots. This step is usually where we get started, and it goes in 2 parts, at least for me, it usually does. First is to actually write the root finding function as a local function. Remember, that always goes at the bottom of the script. The second part of that is to use the script portion, i.e. the top of the script, to plot the function. So all of these problems will look similar in the sense that your root finding function is going to be down on the bottom, and then the actual process of the solution will be up at the top. The function we're going to use to solve for the root is f0. That's the thing that's going to do the iterations that we just saw over in Excel. That's what's going to be finding our solution. And then, of course, we're going to plot slash visualize slash check the solution. Sometimes we'll look at it as a number. Sometimes we'll put it as a plot on or a point on a plot. It just kind of depends. on what we're interested in doing. So steps 1 and 2 is kind of already done, right? We already looked at that twice. We'll skip right to step 3. So 3a is to write the root finding function as a local function at the bottom of the script. So we'll say function. The output is that target value, and the name of the function can really be anything you want, but I have a tendency to call it like RFF or my function or something like that. And remember, it has to be closed with an end statement. And in this case, it's not a particularly complex one, right? The target is the cosine of x minus x. And that's it. That's our whole root finding function. It may require a couple of lines depending on how complicated it is, but it doesn't need to be particularly complicated. In fact, for these kinds of problems where it's something like cosine of x minus x, that's basically one line, what we'll see maybe at the end of next week or the week after that, there's a faster way to write these than local functions that are called anonymous functions. And so we'll get to those later. Now we do 3b. We're going to plot the root finding function. So I'm just going to generate some values of x. We'll again go from -2 to 2 because that's where we went last time. We'll evaluate it. So I'll say RFF of x. So this is generating values from -2 to 2. And then we simply evaluate the function. Actually, we didn't even need to do that if we didn't want to, but sure. We'll plot x and f. I'm going to make it a black line. We should get in the habit of labeling things. It's always a good idea. Personally, I like it when the axis is square and the grid is on because it helps me find values on the plot. So remember this stuff down here, that's our local functions. Everything above that local function, that's where we're actually doing the work of solving something. So if I plot that, I will get a plot that looks something like this. Actually, instead of a y label as y, let's call it f of x. It can be helpful when you're looking for roots for your initial guess to add a line that represents the 0 line. It just sort of depends. I like having a line on there that shows me where 0 is because it's easier for me to find the intersection between those than to keep looking at grid lines. And so we can do that with our hold on and hold off. And there is a function in Matlab that'll just draw a horizontal line for you over any range that you want, and it's y line. So you can say y line of 0. I like it to be kind of obvious, so I make it red dashed. This is optional. I find it helpful. I mean, I guess really a fair amount of this is optional. I would argue that the x and the y label are required, because otherwise you don't know what you're looking at. But I like that dashed red line. It might be a little hard to see on Twitch. I like that dashed red line because it's just a lot easier for my old person eyes to find where is that intersection. Right? That intersection is clearly somewhere between 0 and 1, and you don't have to be too much more accurate than that. So based on this, we're going to guess about 1 for the solution. So this was all step 3. And now we'll go on to step 4, which is to actually do the solving. So we do need a variable that represents our guess. So I'm going to call that x guess, and we're going to set it equal to 1, because that's the value that I'm guessing. The thing that f0 will spit out, f0 is a function, it'll return a single value. The thing that it's going to return to you is your root. And so that is the solution to our problem. I'm in the habit of calling that xsol, primarily to distinguish it from xguess, right? Xguess ought to be close to xsol, but that's just where I'm getting started. Xsol is the solution. That's the value that I'm after. We're going to say that is equal to f0. And f0 takes 2 inputs. The second input is the easier of the two to write. It's just xguess. The first input is a little bit trickier, just because it's using a syntax that we haven't used before. The thing that has to go here is how we tell Matlab, go look at this function that I've written down there at the bottom. That's the thing that you're supposed to be guessing. And moreover, the variable you need to be guessing is x. So how do we tell it all of that stuff? The way that we tell it that stuff is we use the symbol @ which is on your keyboard on the to button. That specifies the beginning of what's called a function handle. The thing that comes after that is what's the variable that Matlab should guess? So it's x. The thing we want you to guess is x. So @x is, this is going to be a function handle for the variable x. And then what function do you want to solve? I want to solve RFF of x. That's probably one of the stranger syntaxes that you'll see in Matlab because it kind of looks redundant. It looks like you're saying @x twice, or you're trying to specify x twice. Remember, this part is saying that's the variable that I want. This part is saying put that variable into this function, right? Guess that variable in this function until that function is 0. This, by the way, is option 1, or let's call this method 1 for F0. We probably won't have time for method 2 today, but we'll come back to method 2 next time. That does the solution, and then step 5 is to verify it. So if we wanted to throw that onto our plot, I'll get rid of a hold off up there, or you can just call another hold on or something like that. If this worked, then what we would expect is if I put xsol back into RFF, I ought to get a dot that looks at it's about 0. So we can say something like plot, the x value should be xsol, and then just to double check, we'll put fsol back into RFF. It ought to be 0. Oftentimes you can just put a 0 there and it'll be okay. It's just another way to double check that you wrote your root finding function correctly. And then I'm going to make it a red dot. So what line 27 says is the x value ought to be our solution, right? That's our function that we're trying to find. That's our root. And if we put that value into our root finding function, we had better get 0 back out. So we're just putting that in there to double check. And now if I run this, we should get a red dot at that intersection, which is in fact what we got. Often we want to know what that answer is though, right? We want to know what the root happens to be. I like to use the fprintf and the sprintf functions because you can throw them onto titles or something like that, and then it makes it easy to see what they are. And also you can mess with the digits that are being displayed, so you can display lots of digits. So I'm going to say a fairly complicated looking fprint function, just so you can see some of the things you can do with it. The first thing I'm going to do is say put a tab in there, which is \t. That means a tab symbol. And then what we want to do is something like f of something 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 is equal to something something something. Remember, whenever we're using these print functions, either fprintf or sprintf, the way to say put a number in there is to start it with a percentage sign and then put a dot on there, or a period, to say this is how many points after the decimal I want. So let's do 6. And the style of number we want is called a float, so it's %.6f. That means put a number in here that has 6 decimal points. And then we want to display next to it another one. We'll say another 0.6f. And then we always want to start, at least with fprintf, a new line after print, so we say /n. That just moves the cursor down to the next line. And then what are the numbers that go in there? Remember, the input order here matches the order in our format spec. So the value that we want inside of there is our root, so that's xsol. And then RFF of xsol goes here. that's one option. If we do something like that and then run it, you should see down in your command window a statement that looks something like this. So f of some value is pretty much equal to 0, right? You ought to always see zeros on the other side. It doesn't really matter how many zeros. I mean, you can go, in this one, I think 10, 12, 15 zeros or something like that, and it'll just keep showing you zeros. The answer that we want, right, the root is this value that's sitting in here, right? That's the 739,085 that we saw over in Excel. Another way to do this that we'll see that's at least worth practicing is the sprintf. And here, pretty much the same thing, right? We can say something like xsol is equal to point, let's say 4f. And then just give it an xsol. That will add the solution directly onto the plot, which is kind of nice. Because now that plot, it's a pretty firm sort of reassurance to you that you've got what you need on that plot, right? The dot looks okay. It's on the 0 line, which it should be, which is somewhere between 0 and 1. And then you look up at the title and you see, okay, the solution's around 7.4 or 7.5. And that looks about where it would be on that plot. And that's it. That's root finding. Like I said, on Friday, we will look at a different syntax for F0, which will help us if we have more than one root. If you have more than one root and you want to use this approach, what you have to do is get your guess close to the root. So if there's a root at 1, a root at 2, and a root at 3, and you give it a guess of 4, it'll always just find the root at 3. It'll never be able to find the other ones until you change your initial guess to get it closer to the root that you're interested in. There's a more specific way that we can do something like that. We can say only look in a particular region, and that's method 2, which really doesn't require too much of a change on here. But we usually use method 2 if we have multiple roots. So I would say this is for single roots. I will come back to method 2 on Friday, because we're about a minute to the end of class. There's no need to cram in one more thing. But reminder, it's almost always going to look like this, right? The pattern is going to look very, very similar as you go through it. Try to resist the temptation of copy pasting old pieces of code. You can look back at them and try to remember what the pattern was, but try to approach each problem by itself, just so that you get used to the syntax. I will not know one way or the other. It's only for your benefit to try to do something like that. I can't tell you how many times in something like 113, students will remember, like, yeah, I did that in 15. Like, now that you showed me, I remembered what it was. But they didn't remember where to go or what the general structure was. They just remembered, like, yeah, we used F0 for something. The more you can stick this pattern inside of your mind and put it somewhere where it's likely to remain, the better off you'll be in future classes. I personally won't know. It's just my advice to you as we go forward. So I'll wrap it up there. If you're on Twitch, I'm also over on Canvas Chat. If you have any questions after I end the stream here, I'll be happy to answer them. Otherwise, maybe I'll see you tomorrow in office hours. Homework 4 is not posted, so there's nothing currently due. So you're not missing anything if you feel like you're supposed to be working on something in here. There's no assignments out. So maybe I'll see you tomorrow, but otherwise, I'll see you back here Friday. Bye, Twitch.